So determining the overall polarity of the molecule is really important in trying to determine the intermolecular forces of a molecule. And the intermolecular forces are going to determine how the overall sample is going to behave, whether it has a high melting point or a low melting point, a high boiling point or a low boiling point. So it basically determines the overall characteristics of the substance itself. Kind of important in chemistry. So intermolecular forces are forces that hold molecules together. Forces that hold atoms together are called bonds. So this is a whole different ballgame. There are three basic types of intermolecular forces. The first type is called a London dispersion force. It's the weakest of the three forces that we're going to talk about. And these are specific to forces that hold nonpolar molecules together. The second force is called dipole-dipole forces, and it's slightly stronger than London dispersion forces, and they're forces that hold polar molecules together. Then we take a look at a special case of dipole-dipole called hydrogen bonding. This is the strongest force, and it's a force that holds polar molecules together, but the molecule itself needs to contain hydrogen directly bonded to either nitrogen, oxygen, or fluorine. And what that does is the electronegativity difference between the hydrogen and the nitrogen, oxygen, or fluorine is so great, it's almost close to ionic. So you have an extremely polarized bond. And when we say polar, we really mean that it acts like a little mini magnet. So let's take a look at each one of these forces individually. The first one, let's take a look at London dispersion forces. When I think about London dispersion forces and nonpolar molecules, I think nonpolar means that the electrons are neither being pushed nor pulled to any one side of the molecule. I like to imagine nonpolar molecules a lot like a jello jiggler. So the electrons are in this field sitting around a center and very kind of fluid shape. So if you'd walk up to it and slap the outside of this jello jiggler, you'd imagine that there'd be a lot of wobble that would kind of start to happen as a result of that strike. And eventually that wobbling would stop and come back to the center. But over time, as it's wobbling, you'd have more jello to one side to the other, and then it would wobble back to the other side. And believe it or not, nonpolar molecules do the exact same thing. As they're flying around in 3D space, they do strike each other, and when they strike each other, their electrons around the outside kind of become a little bit warped around the center, much like a jello jiggler would. So if you want to take a look at what that looks like, instead of the perfect symmetrical distribution of the electrons, we artificially kind of push them off to the one side. That means that we're going to have a partially negative and a partially positive side for a split second. But in that split second, it acts like a mini magnet. And magnets can attract each other, positive side to negative side. So we actually see the molecules starting to line up. But almost as soon as that force lines up and is created, the electrons wobble back and the force is instantly broken. So that's part of the reason why this is considered to be an extremely weak force. It's because these are temporarily turned into dipoles or mini magnets. It doesn't last long. So when these line up on the center, I just thought you'd like to see this, the electrons are artificially pushed to one side. That side becomes partially negative, and then the side that the electrons are pushed away from is partially positive, and these can all line up and interact with one another. So a positive side is going to be weakly attracted to a negative side. And you have this weird lattice pattern that starts to form on the inside of your material. And again, for nonpolar molecules, that's extremely temporary and is broken very quickly as soon as the wobble goes back to the other side. Something stronger, because it's more permanent, happens between dipole molecules or polar molecules. Now, polar molecules have a more permanent distribution of the electrons around the outside, where you have the electrons pushed to one side on a permanent basis. that sets up a more permanent style magnet on the inside of your molecule, a partially negative side and a partially positive side. And just like in the London dispersion forces, a positive and a negative side can attract, and that can set up a lattice pattern on the inside of your substance. Now the difference here is that once this lattice pattern is connected, once it's set up, unlike the London dispersion forces, it tends not to want to be broken up unless acted on by an outside force. Like if I stuck a stirring rod in the center of this material and stirred it, obviously it would break up those forces, but then they'd quickly reform. So let's take a look at the strongest of these forces, and that's called hydrogen bonding. And again, because of the extreme polarity, the extreme electronegativity difference between the hydrogen to oxygen bond here, and that could have been hydrogen to nitrogen or hydrogen to fluorine. It would have worked exactly the same no matter what. We get an extreme attraction from the hydrogen of one molecule, which is very partially positive, to the lone pair of either the oxygen, nitrogen, or fluorine of another molecule. And that's shown here by this dotted line. That's very typical of showing a hydrogen bond. So you usually draw these little like hash marks in between the oxygen to the hydrogen. This attraction is extremely, extremely strong. It works exactly like the dipole-dipole in that the positive side is attracted to the negative side, but it's like a supercharged, superpower electromagnet. It really doesn't want to be disrupted. It's the strongest of the three forces. And again, that sets itself up in a lattice pattern where the positive side of one likes to be attracted to the negative side of the other, and that can set up these weird patterns. Now, specifically for water, that can look a little interesting. So if you take a look at the shape of water, that could actually set up these weird kind of crystal patterns once it actually kind of locks itself into shape. And this is particularly what gives certain ice crystals like snow its really interesting shape. It depends on how the lattice pattern is formed, but you can also notice that the majority of snowflakes are six-sided, and notice that that actually can be boiled down to its internal structure of this weird six-sided arrangement on the inside. So intermolecular forces are actually ridiculously important in trying to describe the behavior of like a macroscopic or large-sized sample, such as a snowflake. So why are these intermolecular forces so important? Well, the stronger the force that holds the molecules together, we get a couple interesting things happening. We can have very high boiling points. In other words, the molecules stick together so well that it takes more and more energy, higher and higher temperatures, to try and rip them apart from each other and get them into the gaseous state. The same thing applies for the melting point, that even in the solid structure, the molecules are held so tightly that it takes all the more energy to rip them apart and to turn them into a liquid. So they tend to have high boiling points and high melting points. They'll have a very strong lattice structure. So in other words, when the molecules are together inside of that pattern, that lattice, it tends to be really, really strong. They'll have something called high surface tension. And if you've ever seen like a water strider actually walk on water, that means that the water molecules have extremely high surface tension. In other words, the molecules almost create this blanket on the top of the surface of the liquid and allow the water strider to walk across it. So the more polar the molecule, the higher the surface tension. You'll also get things like adhesion occurring. So if you can actually stick to other things. Polar things, because they would have this kind of permanent magnet on the inside, tend to be attracted to other magnetic things and can actually stick to them. You'll also have this weird thing happening called cohesion, or sticking to yourself. So because of water's ability to be very polar with the hydrogen bonding on the inside of it, it tends to want to stick to itself, which is why water droplets will have a very particular shape. If you actually just allow a water droplet to form, it tends to have a very a spherical type shape. It's only until it actually starts to fall through the atmosphere that it gets that teardrop shape. The most important of all of these rules is that like dissolves like. So non-polar materials tend to dissolve in other non-polar materials, and polar materials tend to dissolve in other polar materials. This is why you have these weird things like oil and water together. Oil and water tend not to mix. They tend not to dissolve in one another. Oil is extremely nonpolar, whereas water is extremely polar. And the two just can't interact because the water molecule is so busy acting like a magnet and the oil molecule is kind of too busy not acting like a magnet. They just don't want to interact. Whereas if you throw salt into water, salt with its ionic bond acts like a very, very powerful magnet. So does water. So they can actually interact because they're all kind of magnets together. So I hope that this was helpful in trying to describe why molecular shape is so important.